Okay, in this video we'll be going through the 2013 Level 3 Waves Exam. Question 1. Some police forces have used whistles that have two chambers of different lengths. A model of the whistle chamber is shown in the diagram below. On the diagram above, draw the fundamental standing wave in the shorter chamber, and label any displacement nodes and antinodes. Okay, so in the shorter chamber we have a node on this side and an antinode over here. And we know when we have a chamber with a node on this side and an antinode on this side, we have 1/4 wavelengths, and so the fundamental frequency is going to look something like this. And so we can draw that in. And as you can see, if we draw one whole wavelength, we can see if we cut the wavelength in half, that is half a wavelength, and then we have a quarter wavelength right here. And as you can see, that looks very similar to what we have there. That's 1/4 wavelength. The fundamental frequencies of the two chambers are 2163 Hz and 1904 Hz. The speed of sound in air is 443 meters per second. Calculate the length of the longer chamber. Okay, so we know that V is equal to F lambda, and therefore our wavelength is equal to V over F. And now plugging in our numbers, we know our wavelength is equal to 343 all over our frequency, which is 1904. Now the reason why I know that this is 1904 and not 2136 is because I know that length is directly proportional to our wavelength, right? We know this because we have equations like L is equal to 1/2 lambda, right? And L is equal to 3/2 lambda, etc., right? So we have these equations, so that tells us that length is directly proportional to wavelength. Now what we also know is that lambda is inversely proportional to frequency. We can see that through this equation right here. And so from this relationship, if length increases, that means our lambda will increase. And therefore, once our lambda increases, our frequency will decrease. And so because out of these two frequencies, 1904 is the lower frequency, therefore it must be the higher length, or the longer length, I should say. And so that's how I know that this frequency is the frequency of the larger chamber. So now putting that in our calculator, we get a lambda of 0.18 meters. Now again, if we look at our longer chamber, we have a node on this side and an antinode on that side, and therefore we again have a situation where the fundamental frequency is 1/4 of the length. And therefore, as we have the wavelength right here, if we want to find the length, we can divide this value right here by 4, and we'll get the length. So therefore, L is equal to 0.18 all over 4, and this gives us a length of 0.045 meters. Explain how a standing wave is produced in a pipe that is closed at one end. Okay, so if we draw our pipe that is closed at one end and open at the other. Okay, so sound waves are going to enter the pipe from the open end, obviously, because it can't enter from the closed end. And once these sound waves hit the end of the pipe, they're going to go through a 180-degree phase change. And because they go through a 180-degree phase change, they're going to be out of phase with the new wave that is coming in. So, a wave's going to come in, be reflected back out, and as this new wave is reflected back out, obviously the wave is continuous, and so there's going to be a wave coming in. Now this wave coming in is going to be 180 degrees out of phase with the other wave, and therefore that's going to result in destructive interference, creating a permanent node at this end. Now the same thing happens on this side. When we have a wave coming this way, it is reflected back. Now this seems kind of counterintuitive, because if it's an open end, why does it reflect back? Why doesn't it just go straight through? This is because it's changing medium. Even though there's air over here and then air over here, it's the same air. The conditions that the air is in the pipe is different to when it's outside. You can see that the air is confined, and so there's pressure differences, etc. So the medium is changing. Now we know when waves change mediums, there is some reflection, and so that's why some of the sound gets reflected back. And therefore, if the incident wave and the reflective wave at this point right here meet in phase, they will go through constructive interference and therefore creating an antinode at this point. And this is how we get our shape. And so you can write a beautiful answer based on that theory. When the whistle is blown, the sound made is quite different to a pure sound of either 2136 Hz or 1904 Hz. calculate the two other frequencies produced, and explain why these other frequencies are produced, and what effect they have on the sound. Okay, so because these are open and closed-ended pipes, meaning we have obviously an open end and then a closed end on one side, they only support odd number harmonics. And therefore, if we have the fundamental frequency, which we can call F1, the first overtone, which we can call F2, is going to be 3 times the fundamental frequency. And the second overtone, which we can call F3, is going to be 5 times the fundamental frequency. And so for the pipe that produces 2136 Hz, which is the small pipe, the first overtone is going to be 3 times 2136, which gives 6408. And the next overtone is going to be 5 times 2136, and this gives 10,608 Hertz. There we go. Now for the pipe that produces 1904 Hertz, we do the same thing. 3 times 1904, that's 5712 Hertz. And again, 5 times 1904, 9520 Hertz. Okay, so a reason why these different overtones, which are also called different harmonics, have an effect on the sound is because each harmonic can have a different intensity. And it's the combination of these different harmonics and different intensities that create a different sound compared to the pure fundamental frequency. Because if you can imagine, if it was just the pure fundamental frequency being played, that's more of a pure sound and you have obstructions with different harmonics with different intensities, you know? An ambulance with its siren on drives towards a stationary police officer. State the differences, if any, in the velocity and in the wavelength of the sound waves that are observed by the police officer compared to the ambulance drivers. Okay, so this is obviously a case of Doppler, as it says in the question. Now, in terms of velocity, when we're talking about Doppler, the velocity of the wave remains unchanged. So we can write that in, the velocity is unchanged. However, the wavelength does change when you compare it from the ambulance driver's perspective to the police officer's perspective, right? If we are the ambulance driver, put that as a dot. If we are going towards the police officer, which we can call as a square, when we emit wavelengths, we are going to catch up to our previously emitted wavelength. And so the wavelengths at the back are going to be spread out compared to the wavelengths in the front. And so by the time our wavelengths reach the police officer, they're going to be more bunched up compared to the source. And so the police officer observes shorter wavelengths, but we observe the true wavelength, which is the regular wavelength that is unchanged. So police officer observes shorter wavelength. Okay. The ambulance driver drives towards the police officer at a constant speed. Explain why the frequency heard by the police officer does not change as the ambulance approaches. Okay, so this question trips a lot of people up because they go, well, if the ambulance is approaching, then surely there should be a change in frequency, right? Because the Doppler effect. Now, this is true. When the ambulance is approaching the police officer, again, police officer is the square, ambulance is the dot, there is going to be a change in frequency. However, after that change in frequency takes place, there is going to be no change afterwards. So the frequency that the police officer hears is different to the source frequency, but as the ambulance approaches, the frequency that the police officer hears doesn't change. It's different to the source, but it doesn't change. So, the reason for this is because the relative velocity between the ambulance and the police officer does not change. They're moving at a constant speed relative to each other. So the ambulance is moving at a constant speed towards the police officer. And we know our Doppler equation is F dash is equal to the source frequency times the velocity of the wave plus or minus the velocity of the source. Now we're on approach right now, so that means this is going to be a minus. And if the source velocity is constant, so this is a constant value, the wave velocity is constant, and the source velocity is also constant, we can see that the Doppler remains constant. And so, again, to reiterate, even though the frequency that the police officer is hearing is different to the source, so it's the Doppler still takes place, as the ambulance approaches, that Doppler does not change. It remains at, let's say, 5000 Hz. And again, you can write a beautiful answer based on that theory. The ambulance passes close by the police officer and continues past without changing speed. the frequency heard by the police officer changes from 960 Hz to 870 Hz. The speed of sound in air is 343 meters per second. Determine the speed of the ambulance. Okay, so we know our Doppler equation is our frequency of our source times the velocity of the wave all over velocity of the wave plus or minus the velocity of the source. So now, plugging in our information for the approach equation. On approach, the police officer hears 960 Hz. We don't know our source frequency, but we do know the velocity of the sound wave, and that's all over 343 minus the velocity of the source. Again, we're trying to find the velocity of the source, which is the speed of the ambulance, and so we don't know that, obviously. So this is our approach. Now, when the ambulance is moving away, similar equation, but we just flip the sign around. So we have 870, which is the frequency that the police officer hears, and that's equal to our source frequency, which again we do not know, times the velocity of the wave, which is 343, all over 343 plus the velocity of the source, which again is what we're trying to find. Now we see here that we have two unknowns on both equations. So we're like, okay, how do we figure this out? Well, we have two unknowns and two equations, and so obviously we use simultaneous equations. The way I do this is I rearrange for Fs. First thing that we need to do is we need to move our denominators onto this side right here. And so we get 960 times 343 minus Vs is equal to 343 Fs. Same thing over here, we get 870 times 343 plus Vs is equal to 343 Fs. Now, as you can see in our two equations, both equations equal 340 Fs. And so we can make them equal to each other. And so 960 times 343 minus Vs is equal to 870 times 343 plus Vs. Now expanding this out, we get this diabolical number right here, just reading off my calculator, and that's equal to another absolutely diabolical number. Okay, so now that we have one unknown now, because we got rid of the other unknown, we can rearrange to put all the unknowns on one side and all the knowns on the other. And we get 30,870 is equal to 1,830 Vs. And so therefore 30,870 all over 1,830 is equal to Vs. And this gives us a source velocity of 18.87 meters per second. And that is the velocity of the ambulance. The driver of the ambulance then accelerates directly away from the police officer before coming to a sudden stop. Explain how the frequency of the sound heard by the police officer changes during this time. Okay, so we can break this up into two parts. The first part being when the ambulance is accelerating. Okay, when the ambulance is accelerating, the relative velocity between the ambulance and the police officer is increasing. So because the relative velocity between the ambulance and the police officer is increasing, there is going to be a change in the frequency that the police officer hears. Again, if we go back to our equation, this is when the police officer is moving away. So we have Fs times Vw all over Vw plus Vs. Now, if the ambulance is accelerating away, this Vs is going to increase. Therefore, the frequency that the police officer hears is going to decrease continuously as it keeps accelerating away. So again, this links back to the previous question a few questions ago, this one right here. You see how when the police officer is accelerating, that is when we get a change in the perceived frequency. However, again, in this question, it was constant, and so the Doppler remains constant. So for this explanation, we need to say that because the ambulance is accelerating away, the relative frequency between the ambulance and the police officer is going to increase. And also because as the ambulance moves this way, the wavelength that the police officer hears is going to get increasingly long, right? And so because of that, the wavelength that the police officer observes is going to increase. Again, the frequency is going to decrease because the sound wave remains constant. Now, these are two different explanations. The answer schedule explains it using this route right here, where the perceived wavelength is going to increase constantly. But I'm sure you can explain it using this equation right here because it's the same process. But don't quote me on that because it's not in the answer schedule. But it still explains the same thing, so I'm sure you'll be fine. Now, this part 2 of this question is when it comes to a sudden stop. When it comes to a sudden stop, not a gradual stop, the frequency that the police officer hears is going to be the source frequency, because now there is no relative difference between the velocity of the ambulance and the velocity of the police officer. And so the wavelengths that the ambulance produces is not either going to be bunched up or spread apart, it's just going to be the actual wavelength. And so the frequency that the police officer hears is going to be the source frequency. And again, you can write a beautiful explanation with that theory. Jenny is looking through a window at an orange streetlight outside. Many vertical scratches on the window act as a diffraction grating. Describe what Jenny would see when she's looking at the orange streetlight. Okay, so she would see an interference pattern. Apparently that's all you need to write. Just an interference pattern. You don't need to describe what the interference pattern will look like. Just an interference pattern with bright spots and then dark fringes. That's all you need to write. Surprise to me too. Orange light with a wavelength of 589 nanometers diffracts through the window. Jenny measures the first order maximum at an angle of 1.04 degrees. Calculate the separation of the scratches on the window. Okay, so we have our trusty equation, and lambda is equal to d sine theta. This is the first order, so n is going to be 1. We know our wavelength, which is given, which is 589 times 10 to the negative 9 meters, right? D is our separation, and that is what we're trying to find. And so therefore, obviously, because we're trying to find it, we don't have it. But we do have our angle, which is sine 1.04 degrees. And so simply we just divide by sine 104 on both sides, and we get 589 times 10 to the negative 9 all over sine 1.04 degrees, and that's equal to our d. And this gives 3.25 times 10 to the negative 5 meters. Explain why monochromatic light shown through a diffraction grating produces a different pattern of fringes than it does when shown through a double slit of the same spacing. Okay, so this is the case because when we do a double slit experiment, let's say we have a light coming in and we have 2 slits. So these are our slits right here. And we have light coming in over here. When they come in, we know they create like these patterns right here, blah, blah, and they create an interference pattern on this wall. We can imagine these as light sources, right? Even though the source is coming from here, if we were to recreate this experiment with 2 sources, it would look the exact same as this side of the experiment. So we can imagine these as 2 separate sources, and those 2 sources are going to interfere constructively and destructively to create our interference pattern. Now, when we have a diffraction grating, we have essentially way more slits. So a diffraction grating is just a double slit experiment, except now we don't have double slits, we have tons of slits, just heaps of them. So we can conceptualize a diffraction grating experiment as what happens when there are a bunch of light sources interfering with each other. When there are a bunch of light sources interfering with each other, there is going to be a lot more destructive interference, because the likelihood that there are going to be waves that are perfectly in phase is going to be a lot less. So because of that, there are going to be larger spaces between bright spots. So the dark spots are way more dark and way more defined. However, when waves do constructively interfere, they are going to be a lot more brighter, because there are a lot more sources of light constructively interfering with each other. So constructive interference is going to occur much less frequency, meaning there are more dark spots. However, when there are some bright spots, they're going to be a lot more brighter because there are more sources of light. Jenny now observes a white light through the same window. Explain what effect these scratches have on Jenny's view of the white light. Okay, so as we know, white light contains all forms of the visible spectrum. So red, blue, yellow, all that jazz. Now we know that n lambda is equal to d sine theta. We can assume n to be the same. Now if we just talk about the first order, so n is equal to 1. So basically we can just remove n. We know that the different colors of light have a different wavelength, right? We know that red has a different wavelength, or should I say a longer wavelength than blue, right? So if we put white light through a diffraction grating, which again, white light is just a combination of the entire visible spectrum, because all the colors are just going through one diffraction grating, d is constant, and so we don't have to worry about it in our analysis. So now we just get the wavelength is directly proportional to sine theta. Now we know that red has the largest wavelength, so lambda is the greatest. If the lambda is the greatest, that means sine theta has to also be the greatest. And so what you will see is that red diffracts the most. And we know that violet has the shortest wavelength. And so violet will diffract the least. That's not how you spell least. There we go. And so because red has the largest wavelength, the angle at which it diffracts is going to be larger compared to violet, which will have a smaller angle of diffraction. And so what you will see is you would have a middle point of maximum, which is just going to be white, right? N is equal to 0 is going to be white light. And you'll see a visible spectrum on either side. And in the spectrum, you're going to have red on this side and violet towards the center. And the rest of the spectrum is going to be in between. And with that, we are done.